Second-order system response. This lecture will build on what we saw last lecture in first-order system response. We're still looking at applying a step input into our systems, but now our systems are going to be of second order. So at the end of this lecture, you should be able to put our second-order systems into the standard form. You should be able to identify the parameters of the system. It's going to take typically 4 of them for our second-order systems. From here, we're going to be able to classify the stability type we have when we're in transfer function form, and then later in the lecture, we'll get into state space form. And we should be able to sketch the response of our system due to our step input. And later in the lecture, we're going to see what happens if we have a third-order system or a second-order system with a 0, how that's going to change the behavior of the response. So we can start looking in the time domain as to how our system is going to respond. So this is a general second-order system differential equation that we see. We have an x double dot, we have an x dot term, and then in general, our right-hand side is this f of t. Again, in this lecture, we're only going to look at step inputs on our right-hand side. So if we have a step input of magnitude of b, then we can say it's b times 1 of t. Again, 1 of t is just the step function. And this is a second-order system that you saw before in Math 251 in your ODE class. So we can get a general solution to it. So one way we could do that in the time domain before we knew anything about using Laplace transforms is for a second-order system, we could find the roots of that characteristic equation. So if you remember, we can set the x double dot to like lambda squared, x dot to lambda, and set the right-hand side to 0, and we can solve for the lambdas. And if we do that for any second-order system for the homogeneous solution, then we see that the lambda is equal to this. So it's this negative omega n zeta plus or minus this square root term. And what we can do is we can take those lambdas, and this forms our general homogeneous solution, where we have an unknown coefficient times e to the negative lambda 1, and another coefficient e to the negative lambda 2. And what you can do is once you have initial conditions, once we have our particular solution, we can get our total solution and apply initial conditions. After applying our initial conditions, we could find those C1 and C2 terms. However, we're right now looking at the bigger picture, those lambda values that we have in the exponents. We know from Math 251 that the lambdas tell us about the stability of the system, because usually what we saw is that if our lambdas were complex, a real term and imaginary term, we wouldn't use this as our general homogeneous solution. We would have a sine and a cosine term. And the sine cosine trig terms are going to be periodic, and that's why we're going to see oscillations, as we'll see later when lambda is imaginary or complex. However, when lambda was real, then we would use the form like we have here, and we would say, oh, okay, it's 2 exponentials that we're adding together. We're going to later see that lambda being real, either repeated or unique real values, is going to give us no oscillations in our system. We're going to see that unique values of lambda will give us an overdamped system, and repeated values of lambda will give us a critically damped system. So the big takeaway for now is that value of lambda, whether it's complex or real, is going to tell us about the stability of the system. Now we'll go transition back into talking about our transfer function form. So as we saw in Unit 1, we can put a second-order system into transfer function form. So we take the Laplace transform like we have before. So where we're going in this lecture is, once we're in this transfer function form, we want to be able to analytically make analyses of how our system is going to behave in the time domain, very similar to what we did in the previous lecture for the first-order systems. And second-order systems are going to come up very often because a spring mass damper system or an LRC circuit is going to be second order. Now, if we have additional masses or if we have additional elements in our electrical system, we can easily get to third, fourth, or higher order systems. But for second order systems, we're going to cover a lot of what we see in this course. As we get into control systems, we're going to see that treating things as a second order system can be helpful. In this unit, we're still talking about what I'm calling passive control, where we will have, we might be able to select different masses, dampers, and springs, or we can select different inductors, resistors, capacitors that will actually change our transfer function and thus change the behavior of our system after a step is input into it. Again, in Unit 3, we'll talk about active control and how there's different strategies to get a desired behavior. So like we saw with the first order systems, what we're going to need to do in order to make a sketch and to do some analysis is we need to get our transfer function into this standard form that we're going to use for our second order systems, as indicated in the highlighted portion for G. So notice the important thing we have here is that in that denominator, the leading coefficient in front of s squared is 1. If it is not 1, you're going to have to divide everything by that coefficient to rewrite our transfer function so that it is 1. Once the leading coefficient is 1, then we can look at the rest of these terms. So in front of the s term, we're going to have this 2 zeta omega n, and now our constant term is omega n squared. And then the numerator is going to be an a times omega n squared. So we see 3 parameters here that we're going to need a, zeta, and omega n. So we have our standard form. So what do these things actually mean? So omega n is what we call the natural frequency of the system. And you should have seen this before in Newtonian physics. Zeta is what we call the damping ratio. And then it doesn't appear in our transfer function, but we are going to be using this to do some of our sketching, is we have omega d, which is the damped frequency. Now this only comes up if we have an underdamped system, which again, I'm going to define a little bit better in a minute here. But we have our natural frequency, damping ratio, and then we can combine those to calculate the damped frequency. Right, so as far as the response goes, if we have our input, again, is this amplitude of b times 1 of t, then the first thing we can see is what is the steady state value of our system going to be. And actually, it's the same equation we saw for a first order system. It's the a as defined in this transfer function above times the amplitude of our step input. Now, what does the damping ratio tell us about the system? I alluded to it earlier when I was briefly talking about our time domain solution. So let's see what they are going to tell us. So if we have a zeta value that's less than 1, and technically it's between 0 and 1, we're going to assume our zeta values are positive for right now. So if we have a zeta between 0 and 1, that indicates that we have an underdamped system, which means we are going to see oscillations around that steady state value. And if we go back to the time domain solutions, a zeta less than 1 gives us a negative number inside that square root, and thus that's why we're getting we would get a complex value for the characteristic, the roots of that characteristic equation. If we get zeta equal to 1, we have a critically damped system. We will not see oscillations around that steady state value. And going back to our time domain solution, this is going to give us repeated roots of lambda. Or we could have a zeta greater than 1, which would be an overdamped system. And again, we would have a lambda here, which would be real but unique roots. Linking together the transfer function and what I was talking about earlier in the time domain, if we look at the poles of this transfer function, we get negative zeta omega n plus minus, really that's the damped frequency, is that second term. The poles of the transfer function are exactly the roots of that characteristic equation. Right, so once again, from the previous slide, this tells us that we have complex poles if zeta is 0 to 1, real repeated poles if it's 1, and real and distinct poles if it's greater than 1. So again, it makes the poles of the transfer function the complex, real, or repeated. Now here I allow for what happens if zeta is 0. Well, we see the poles are going to be purely imaginary because that real part is going to be 0. We're not going to really see this coming up in this class, or once we get to control, we want to avoid this. This is a neutrally stable system. And then if we have a negative value of zeta, we see that the real part of the pole is actually positive, and the poles are in the right half plane. And thus, our system is going to be unstable. Thinking all the way back to when we talked about initial value theorem, final value theorem, the first thing we had to look at was, Are the poles all in the left half plane? Are they all where this green text is? If so, then we're going to reach some steady state value given enough time, either asymptotically or maybe it's going to oscillate around it. But what happens if zeta, if the poles are not only in the left half plane? Well, then we're in the yellow or the red situation, and we're going to see that given enough time, no, we don't get to some constant value. It's either going to keep oscillating if zeta is 0, or it's going to blow up to positive or negative infinity if zeta were negative. So what does a typical response look like in our system? So here we have two systems. I'm not showing what the actual transfer functions are, but let's say we made our transfer function and we found that value of zeta. So in the one on the left, we have a zeta greater than 1 or equal to 1. It's, again, generally going to look the same if it's critically damped or if it's overdamped. So we see we're starting at 0. We apply the unit input into our system, and now we are asymptotically approaching some steady state value. Here it's around 0.17, but the important thing is, notice on the left, we don't oscillate around that steady state value. We're in this case approaching it asymptotically from below. And in contrast, on the right, we have a system where we have a zeta between 0 and 1, indicating that it is underdamped. So in this system, we're starting at 0, we apply our step input, and now you see that around 1.5 seconds, we are what we call overshooting the steady state value, and then we go back down. We actually go below the steady state value. It's tough to see in the picture here, but we go a little bit below, and then we're going to oscillate around it, and those oscillations are going to get tighter and tighter around the steady state value as time goes forward. And we can see here if zeta is 0, we have a neutrally stable system, and we see that those oscillations are not dying out. This is a case where we would have an undamped system. That would cause zeta to be 0 if our damping coefficient were 0. So no energy is being added to the system or taken away from the system, and we just infinitely oscillate between some maximum and minimum. So the system is not stable. It's neutrally stable. It doesn't go to infinity, but it also doesn't go to some constant value. And on the right-hand side, we have zeta less than 0, an unstable system. So mechanical systems, really, we wouldn't see this happening because it would be like a damper that's adding energy into the system. But there are systems we can model where effectively it would have a negative value of zeta. And we see here, as time goes forward, the amplitudes just get larger and larger and larger, and will blow up to a positive infinity or a negative infinity. As a little cartoon here, we can see where the pole location is and how it's going to affect what the general shape of that output function. So again, in the left half plane where we have stability because the poles are in the left half plane, if we are on the real axis, meaning we are purely real, then we are going to asymptotically approach our steady state value. Once we have a complex value, we're going to have those oscillations. And as we move on to the right-hand side poles, then we go into the realm of instability or having an unstable system.